Biological and social systems are the most highly ordered, the most complex phenomena we know. Their complexity and order have been increasing for several billion years. In other words, while the second law of thermodynamics says that the universe is becoming steadily more disordered, we are ourselves part of a system that is growing more ordered. If we seek a deep understanding of living systems, we must at some level refer to the laws of physics. But we've seen that the physical law that's most pertinent to biology, the second law of thermodynamics, is thought by many physicists to be essentially a statement of our ignorance. If they're right, then the laws of physics would not provide a very firm basis for our understanding of life. Ilya Prigogine is not content to leave the law in the hands of the physicists. Instead, he works to show that we're not simply expressing our ignorance when we say time runs in one direction only. Prigogine says that the irreversibility of time is a fundamental property of most dynamical systems, and indeed of our entire universe.
Most systems of interest to us, including all chemical systems, are time-oriented on the macroscopic level. Far from being an illusion, this expresses a broken time symmetry on the microscopic level. Irreversibility is either true on all levels or on none. It cannot emerge as if by a miracle, by going from one level to another.
Prigogine tells us that time is not symmetrical, that most things cannot run both backward and forward. And when we step out of the conceptual straitjacket of time reversibility, we are opening ourselves to time, to change, to becoming.
We are discovering the primacy of time and change, from the level of elementary particles to cosmological models. Both at the macroscopic and microscopic levels, the natural sciences have thus rid themselves of a conception of objective reality that implied that novelty and diversity had to be denied in the name of immutable universal laws. They have rid themselves of a fascination with a rationality taken as closed and a knowledge seen as nearly achieved. They are now open to the unexpected, which they no longer define as a result of imperfect knowledge or insufficient control.
Ironically, Prigogine's primary goal is to show how the law of increasing disorder actually is responsible for the ever-increasing, ever more complex order that we see all around us. More specifically, Prigogine says paradoxically that non-equilibrium is the source of order.
At all levels, be it on the level of macroscopic physics, the level of fluctuations, or the microscopic level, non-equilibrium is a source of order. Non-equilibrium brings order out of chaos. But the concept of order, or disorder, is more complex than was thought. It is only in some limiting situations, such as with dilute gases, that it acquires a simple meaning.
Prigogine's concern is not with the ordinary physical laws of being. That's the domain of physicists. He wants instead to know the laws of becoming, the laws of creation, evolution, and change. His work has produced what he calls the theory of self-organization of far from equilibrium systems. What does he mean by this phrase? We've already discussed the idea of equilibrium in general, represented by the marble at the bottom of the bowl. But Prigogine is referring here specifically to thermodynamic equilibrium, that is, the equilibrium of complex physical and chemical systems. A good example of thermodynamic disequilibrium is a cold drink with ice cubes in it. If we don't drink it right away, the ice melts and the drink becomes tepid. It warms up to room temperature. The system consisting of the room and the drink is now in thermodynamic equilibrium. This is what physicists call the state of maximum entropy, meaning maximum disorder. The earlier complexity and organization of different substances, different temperatures, and different shapes has now evolved into sameness, into a lack of organization and complexity. Notice that the system is predictable. If there is no outside disturbance, we can predict with certainty that whatever the initial temperature of the drink, it will eventually reach room temperature. In thermodynamic systems, this means that the system's history, its initial conditions, and its record of development over time is lost. As Prigogine puts it,
in an isolated system, all non-equilibrium situations produce evolution toward the same kind of equilibrium state. By the time equilibrium has been reached, the system has forgotten its initial condition. That is the way it had been prepared.
Let's look now at a similar but much larger system, the Earth's atmosphere. Because it is heated by the sun, very unevenly, with more heat in the tropics than in the polar regions, the atmosphere is very far from equilibrium. But like the warm room containing the cold drink, it tries to reach equilibrium by transporting heat from warm to cold areas and by radiating heat into space. The result is a complex pattern of atmospheric circulation, which we experience as the weather. The atmosphere is a self-organized system. Within the global circulation pattern, we can identify very well-defined large-scale structures like storm systems with warm and cold fronts, hurricanes, and tornadoes. A tornado is a sort of runaway convection current, and it's a very well-defined object. We can see it, photograph it, watch it destroy houses. Yet, like all convection currents, it is nothing more than a collection of atmospheric molecules that have organized themselves to circulate rapidly in a spiral formation. There is no overall plan for the tornado. There is no overall manager to ensure that the molecules circulate as they should. The organizing process operates entirely at the microscopic level of one molecule jostling another. As Prigogine points out,
the system behaves as a whole, as if it were the site of long-range forces. In spite of the fact that interactions among molecules do not exceed a range of some 10 billionths of a centimeter, the system is structured as though each molecule were informed about the overall state of the system.